Hello everyone, this is 𝐿𝐿𝐿 𝐿𝐿 and I am back with another discussion video. Today we will be discussing about WebSockets, how they can prove to be costly. So we generally discuss WebSockets in the context of persistent connections whenever we are trying to build chat applications, okay, similar use cases, whenever we want to send some data from user devices to server and then send some data from server to user devices. So these kind of persistent connection we are trying to maintain, okay. So in these kind of purposes, we tend to use WebSockets. Now there is one specific use case which we are discussing today, in which we will try to understand how they can prove to be costly, and we will have to explore other alternatives to replace those WebSockets. Okay, so this is a blog by Recall.ai. Recall.ai is a software which can be easily integrated with platforms such as Zoom or Google Meet, Microsoft Teams, okay, these kind of meeting softwares which we generally use in our companies. And after it kind of, you can say, joins as a bot in your meeting, and then it can provide you details like transcript, meeting recording and all those things. So this is the basic purpose of Recall.ai. This is not a promotional video. We will try to dive deep into the blog which is written by them, and try to understand what were the issues in their architecture and how they actually solved that architecture, how they improved that architecture to resolve the bottleneck. So the heading, WebSockets are costly. I really like the way the blog is written. So let's get started. But before that we have to do something which we always try to do, which is promotion. Promotion of what? Promotion of MsDeep Singh. Now MsDeep Singh is great person who try to publish lot of educational content. Now this is the channel MsDeep Singh, where you keep on learning about system design, distributed systems, and not distributed systems per se, but how to build simple and scalable systems. So that's our main motto. Our main motto is not always to build a distributed system. Our main motto is to build a simple and scalable system. If that's distributed, then we will do that. So consider subscribing. You will learn a lot of things. After watching this video, you will know that it's a great channel to learn things about system design. Apart from that, consider looking into the book System Design on AWS. The content is already completed. By the time the video will be out, you will have this book available on Amazon and other platforms. You can also read it on the O'Reilly platform. This book has also detailed chapters on how you can use WebSockets and what are the different use cases, purpose where you use WebSockets, and then we also have this in application, how you actually. So first you have to understand what WebSockets are, and then you will have to understand how you can apply them in actually application building, actually system building. There is also a video around, not a video, content around, chapter around video processing pipelines. So if you look into this Recall.ai use case, okay, they are consuming those videos, okay, whatever is happening in the meeting, and then it is processing that video to finally produce that transcript or meeting recording. Okay, so you have some sort of video processing pipeline in picture which does all this job. So we'll try to understand that as well in the chapter. Okay, so consider looking into this book System Design on AWS. You will soon have the physical copy available on Amazon and other platforms. You can go buy and also check out online if you love reading online. Okay, so as always, what is the first thing we should try to do? What is the first thing we should try to do whenever we are trying to build the system? So in this case, the system is already built, okay, and our main motivation is somehow we want to try, or somehow we want to ensure that the cost is reduced. Okay, so Recall.ai is using AWS Cloud to host their infrastructure, and this infrastructure is the cost AWS cost is quite heavy, okay, quite huge. So how can we reduce them? So let's talk about the existing architecture, and then we will try to understand how we can come up with the improvements. Great. Okay, so Recall.ai powers meeting boards for hundreds of companies. It has video processing on CPUs. They do not use GPUs because some of the reasons mentioned were that, like, GPU is not kind of patchy on the cloud provider, so they still use GPUs for video processing. Now each board each meeting board requires 4 CPU cores to run efficiently. Okay, all the operations which are done by this board, it requires 4 CPU cores to run efficiently, all the processes which has to be done. Great. Now this architecture which I have drawn with the help of Recall.io, this was not available on the blog, so this I just added it as per my understanding how it could look like. Okay, the architecture of Recall.ai can be totally different, but this is the basic gist or the idea which you can see that it will be much similar to this. So the idea is you will know that you will have to join some meeting. How will you know? Okay, so let's say some meeting is happening on this zoom.s and this is meeting ID. Okay, now this meeting board along with the other attendees of the meeting will also get an invite. So let's say you will have some systems, you will have some system which has this information present, what all meetings are happening. Okay, so that this meeting bot can join that meeting and then do that other video processing work. So you have some sort of scheduler which asks this meeting application that go join that particular meeting. Okay, this meeting application will try to join this meeting. Now how will this meeting application join the meeting? Okay, so the way it is done, let's talk about me. How will I join the meeting? I will open my browser and then I will go to that link and then I will join the meeting. Okay, similar functionality we are trying to do here. What? So it spun up a Chromium browser. Okay, it spun up a Chromium browser, and generally if you use Chromium in, let's say, launched on a machine and then you do some operations, let's say joining of meeting and all, it's generally called headless Chromium. If you are from QA background, you will easily understand that you spun up is Chromium browser, not Chromium specifically. You can spun up any browser, but it is generally called headless deployment, in which the Chromium is spun up and then the application is run. Okay, this is generally used for running the integration test when you try to understand how the users are using your application. Okay, so this is much similar concept here as well. So you spun up Chromium, then you join the meeting. Okay, the meeting bot will join the meeting on this browser. Great. So this meeting bot is much similar to a person joining a meeting. Okay, on his browser. In this case, a meeting bot is joining a meeting on this Chromium browser. Great, we are cool with this. Now once this is done, you again comparing with a person, you will participate in that meeting. Okay, you will participate in meeting to contribute in something. Meeting bot will just listen to the meeting, what is happening in the meeting. It will not say anything per se. Okay, so it will just try to listen whatever is happening in the meeting and then consume those video frames and audio from different persons in that meeting, and then further pass it for the further processing, let's say creating meeting or transcript, creating recording or transcript, or like any other purpose. Let's say you are using it for translation, real-time translation. Okay, so there are multiple use cases, but the idea is same. This Chromium browser will establishes a WebSocket connection with a video processing pipeline. Okay, so this is your video processing pipeline which I have drawn. So this Chromium browser, a meeting bot which is running, some thread is running on this browser which continuously consumes the video frames and then sends to the video processing pipeline. These frames are sent to the video processing pipeline, and to avoid that you have to establish connection again and again, you can use TCP, right? You can use the TCP connection, but in the TCP connection you have an overhead of establishing that connection again and again. So what you need that connection is established once. Okay, connection is established once, and then once it is established, then you can continuously transfer the data, so you don't have that overhead of establishing the connection again and again. Great, cool with it? Great. Now once this is done, the video WebSocket connection is established, what you do, this video uploader component, the frames will be passed here. Okay, this WebSocket connection with frames will be passed here, and then it is uploaded to some, let's say, object storage, and then you have video encoding. Why do you have video encoding? We have created a video related to Netflix video onboarding architecture. Okay, there is two videos in the Netflix series. One talks about how videos are uploaded on Netflix, and another video talks about how these videos which are uploaded are streamed to the users. So go check out those videos. Now the idea is pretty simple. Okay, what we mean by encoding is I will quickly explain you. So in case of encoding, what happens is there are a lot of devices. Okay, there are a lot of devices which are available across the world. Okay, and apart from devices as well, there are different internet bandwidth which can be supported by the users. Okay, let's say I can only afford 4G. Okay, but you are a premium user, or you are very rich kid who can afford 5G. Okay, or you have like that fiber net Wi-Fi. Okay, so it depends, right? It depends on the use case, or like how much money you have. Depending on that, you have that particular kind of connection. Okay, and depending on that, you have that certain kind of devices. So the idea is you have multiple kind of devices, let's say smart TV, let's say mobile device, and on these different kind of devices you have different formats which are supported for a particular video. Some supports MP4, some supports M4V. Okay, so some supports MOV. So these are the different formats. I'm not sure this is the format actually which exists, but there are different formats, right? There are different formats which are available, and then there are different resolutions. Let's say 1080 pixel, okay, 144 pixel, okay. As I said, right, depending on the internet. So that's how your encoding is helpful. What you do, you try to capture that video and then encode it into multiple formats. You will also compress it definitely. So the video which you have received earlier, okay, the video which you received earlier was, let's say 100, not, let's say 1 GB. Okay, so you have to compress it so that it is much similar to, let's say, 10 GB. Okay, so you have to do compression, you have to do encoding, and once that is done, you have this processing components, as in you have some component which does all the tasks, such as, let's say, create a recording, okay, in different formats, and then you have transcript generation. So there can be different use cases. Okay, so this is the existing architecture of our system of Recall.ai. You consume the data from whatever meeting is happening. Once that is done, you do the further processing. Now we mentioned that now coming back to our requirement, what we want, this is working great, there is no bottleneck. The only bottleneck is we are paying a high bill to AWS. We want to somehow reduce that bill. So if we want to reduce that, we are saying that we are using 4V CPU. Okay, we are using 4V CPU. If you can reduce that 4V CPU to 2V CPU, then you can say that your cost will be reduced, because you have reduced the infrastructure cost by half. Okay, great. This is what we have to do. So we have our motivation clear. What's our motivation? To reduce those infrastructure nodes which you are using. Okay, so let's say you are using earlier 100 nodes, you have to do all those operations within the 50 nodes itself. So breaking the cost, or like breaking down the cost by 50%. Okay, so let's understand what CPU is actually doing. If we want to reduce the cost of CPU, then we have to understand what CPU is using, or like where that data, or like that processing power is spent on, computation power is spent on. What is the first thing which comes to your mind when you say I'm doing a video process, I'm managing a video processing pipeline, and this is the CPUs which I'm using? The first thing which comes to your mind, that you can assume that yeah, it's a video processing, so it will take a lot of processing power. Okay, so that's your inherent assumption, that you have your encoding and decoding tasks which are happening, and those are the tasks, those are the threads, those are the processes which are consuming my resources or consuming my computation power. But we have to make that we have to say that with 100% surety that yeah, this is the case which is happening. Now how you can do that? You run a profiling. Profiling is a way which you can run for your programs to understand what you're actually, like, where your threads are actually spending their time. Okay, so that's what responsibility, or you can say functionality, you get out of profiling. There are different profiling tools available. I'm not sure which tool they used, but there are different profiling tools available, and they are very much specific to languages, because the threads, or like the processes on which these application threads run, vary depending on the programming languages. Great. Now after running the profiling, these are the two methods which were called at what you can say at high rate. Okay, so these are the two methods on which CPU spent most of the time. What is the method? One is memmove and another is memcpi. These both are related to copying blocks of memory. Okay, these are the C functions which are responsible, or you can say used for copying blocks of memory. And this suffix which is there, AVX, unaligned, ERMS, this is written specific to a specific processor. Okay, these are the library methods from C which in short are responsible for copying blocks of memory. Okay, now we have to understand if these methods are called so many times, if the rate is high, from where they are called. Okay, you will have to understand that. So figure out that. So where they are called from: Python WebSockets to receive data, Chromium WebSocket implementation to send data. Okay, so these functions are called specifically in this pattern. Okay, in this pattern. This WebSocket connection is established, Chromium is sending some data, and this video processing pipeline is receiving data. So this is where your functions are called. What is happening in this function, or like what is happening here? Why do they need copying of data? So we'll have to understand that. So let's get more into the detail why this is happening. Okay, WebSockets dive deep. So bots, if I quickly summarize like what these bots are doing: bots join the call using headless Chromium. Okay, great. This is the operation which is handled, and then you transport raw decoded video from Chromium's JavaScript environment to encoder. Okay, so this is the operation which I am saying. Okay, so raw video, okay, raw video is transferred to video encoding component. Okay, this is the function, or these are the two methods in which these two are called. So if I talk about what is the data which is being sent, the data which is being sent is around 150 MB seconds of video data. Okay, this is the P99, so it's 150 MB of second, 150 MB per second of data which is being sent by here. Okay, so what's the reason for this? Okay, we will have to understand the reason, right? So there are two reasons specifically. First is fragmentation, another is masking. Okay, fragmentation basically means you have a large packet and then you break it into multiple chunks. This is fragmentation. Masking basically means you have these bytes of data, right? 0, 1, 2, 3. Okay, so you are masking this data. You are masking as in something similar to encryption. Okay, so I'm masking this data by joining the bytes of this data by some random key. Okay, this is what these two operations, and these two operations are responsible for this high invocations of WebSocket API. Now fragmentation, large messages split into WebSocket frames. Okay, for Chromium WebSocket implementation, messages larger than 130 KB, 131 KB is fragmented. So if we talk about, like, let's say a 180p raw video frame, the single video frame is approximately 3 MB. Okay, a raw video frame is approximately 3 MB, so it will be split into 24 WebSocket frames. Okay, great. And another thing is, this means a lot of copying and duplicate work. You understood it, right? Masking, as I said, what to do and this is the feature of WebSocket basically, that the data which is sent over a WebSocket wire, it is masked first. Okay, so data from client to server must be masked. This is a must requirement. If you are using WebSocket, this is going to happen. Obtain a random 32-bit masking key and join the bytes of original data with the masking key, and this masked data is sent on the WebSocket wire, okay, to the receiver's end. Downsides of masking: you will have to iterate over this data to mask this data. Okay, so this might not be a bottleneck for features in which there is no heavy copying of data which is being done, but in case of, like, let's say this 150 MB data per second, this is the huge work. Okay, so this is why the reason, or like this is the main reason why is this issue is happening. And when I say copying of data, right, this copying of data basically means this application or this meeting bot, let's take this, let's say this is your operating system. Okay, this is your user space and this is your kernel space. Okay, so your protocol works on the your networking stack basically works in the kernel space, and your meeting bot is running in the user space. Okay, so whenever the data is being transferred, you will have that data copied from here to here. Okay, the data is being moved from user space to kernel space. Okay, so in case of fragmentation, when I say fragmentation, your all the fragments will be copied to kernel space. Okay, when I say masking, this again, you will have to iterate over each and every byte, and then you will have to mask that data. So these two are basically causing the issues. We have to fix that somehow. So what could be the other transport options? We mentioned that WebSocket is a problem. WebSocket, why? Because we have fragmentation and masking in place in case of WebSocket, which we can't skip. So we have to figure out some other transport options which we can use here to resolve our issue. So what are the other transport options which were explored by Recall.ai? First one is TCP/ID, TCP/IP. Another thing is Unix domain sockets. Third is shared memory. Let's talk about each and every of them. TCP/IP. Now, in case of TCP/IP, okay, TCP/IP is a great protocol to use, but the problem here as well is, first thing is, which we discussed at the start of the video, what? That you will have to establish the connection again and again. Great. You will have to do that. Another thing is, it will also lead to fragmentation. Okay, so in case of TCP as well, you can't send that single that video frame in one go. Okay, that will be segmented and segmented. Okay, fragmented basically. Yeah, it will be broken down into chunks, and maximum transmission unit is 1500 bytes. So the segment size is approximately 1448 bytes. This, if you paid attention in your college, in your networking classes, you have seen that TCP block diagram, right, in which you have different kind of headers and all those things, and one specific component is that where their actual data is present, which is this segment. So this is the segment 1448. Rest of the around 50 bytes are used for other purposes, for other information, such as like what was the total size and all those things. Great. So it is much smaller than 3 MB raw video frame. So again, we mentioned that this video frame, right, this one particular, approximately it's 3 MB in size. So it will be fragmented, it will be broken down into chunks, multiple chunks. So again, you have that same problem. Okay, and as I mentioned earlier, Linux networking stack runs in kernel space, means TCP/IP runs in kernel space, means packets needs to be copied from user space to kernel space, which adds the significant overhead. So we have two problems here. In case of TCP/IP, we can't use it. Okay, what's the another option? Another option is Unix domain sockets. So what you are doing here, you are exiting the network stack and you are using the Unix domain sockets. Now, to send data through Unix domain socket, data needs to be copied from user space to, so you don't have that overhead of fragmentation, but still the data will be copied from user space to kernel space. Okay, you understood that idea, that your program, your application is running in your user space, and then you are copying the data from there to your kernel space to send the data. Okay, shared memory. Third point is shared memory. So in case of shared memory, what you are trying to do is, okay, so from the first 2 points, what you understood, from the first 2 points, the problem is the data copying is happening. Okay, and you want to avoid these operations. Basically, you want to avoid these operations. Okay, how you can do it? You have to avoid these two operations, and if you say you want to avoid these operations, you have to avoid copying of data which is happening. Okay, copying of data which is happening. So shared memory can be a particular implementation which can be used because it can be accessed by multiple processes at the same time without requirement of copying of data. Okay, so the problem is copying of data. So use shared memory accessible to multiple processes at a time. Chromium writes to a block of memory and this is read directly by video encoding, no copying required. Okay, problem, there is no transportation. This is the problem. That there is no default transport mechanism which is available, which can be directly used. So you have to somehow implement your own. You have to come up with your own implementation to use this shared memory functionality. So how it is implemented? Let's discuss how it's implemented. But before that, we have to understand what are our requirements, what are our use cases. Okay, you have to, before designing a solution, you have to come up with the requirements, that these are my requirements, and for these of my requirements, this is the solution. So what are the requirements? The first requirement, the main requirement, is there is continuous read and writes happening. Now, what are the functionalities we need? First thing is lock free. Okay, lock free as in the data is not locked per se. Okay, the data can be continuously read without needing lock. Okay, so consistent latency and no jitter okay, this is the one of the use case that transcript of video is generated in real time, so it should be fast. Okay, the latency should be predictable. Great. Multiple producer, single consumer. There are multiple threads which are writing the data. Why multiple threads? Because some thread is running the audio, writing the audio data, some thread is writing video data. Okay, but there is a single thread which is reading the data, which is our encoding component. Okay, now dynamic frame size. The frame size can vary. Why it can vary? Because the video format can be of different formats. Okay, that is first thing. Another thing is why it could be of different formats, because we have different devices to support. Another thing could be we are supporting both audio frames and video frames, so the frame size could vary. 0 copy reads. We don't want to have any copies available. We don't want to have a requirement that we need a copy. Okay, so that's one of the thing. Sandbox friendliness. Chromium threads are sandbox, should be able to easily access ring buffer. Ring buffer is the solution which you are going to use. So sandbox is basically, you can say, an environment in which the Chromium is spun up. Okay, so that's what we mean by sandbox. Okay, low latency signaling. Another thing is that whenever the data is returned, we want some kind of event mechanism that, yeah, data is written, now you can read it. Okay, some kind of event mechanism we need. Okay, so this is what we mean by signaling. Chromium reads, this should be signal to media pipeline when new data is available or no buffer space is available. So in both of these scenarios, it should produce the signals, and media processing or like any of the consumers can know that, yeah, this is the signal which I have received, and accordingly I can, if I have to take any actions, I can do that. Transport design. Now let's talk about the implementation. So for implementation, ring buffer is used. Now before exploring further, let's understand what ring buffer is. Ring buffer is basically your circular data structure. Okay, circular data structure in which data is written. Okay, so when I say circular data structure, you can assume it is circular linked list. Okay, circular linked list. It's a FIFO. Okay, first in first out. So last element of buffer is connected to the first element. It is of fixed size. Okay, this is of fixed size, so something of this sort, right? And it has 2 pointers which is not written here. Yeah, it is written here. Implemented with 2 pointers. One is start and one is end. Okay, so where the first data point is written, and is like where is the most recent data written. Okay, useful in real time. And this is the use case or like of real-time systems, that whenever the data is written continuously, and if we have if our use case allows that data can be overwritten, then we can use it, because we have a limited size. It can't be a keep on expanding. So once the size is exhausted, you can overwrite the data which is already present, because it was transferred to the consumer. Now the problem is the default implementations which are available do not support all the features which we need. Okay, all the features we need. So there is a custom implementation which is written by Recall.ai. The implementation looks like this, and it uses 3 pointers basically instead of 2, which we said here, start and end. It uses 3 pointers. So you have Chromium. Okay, this is your Chromium as we discussed in our architecture. This is your Chromium. Your frames are passed. Your frames are written into this ring buffer, and then they are consumed by this media pipeline, and finally a recording or your transcript is generated. Great. Now if I talk about the 3 pointers which are mentioned, what are these 3 pointers? These are 3 pointers. One is write pointer, second is peek pointer, third is read pointer. What we mean by write pointer? Write pointer basically mentions that where the data can be written. Okay, so these frames will be written by the write pointer at the place of write pointer. So write pointer is your basically address on which the data can be written, data to be written. Peek pointer, address of next frame to read. Okay, peek means basically looking, peeking. Okay, so where this media pipeline can look for data. Okay, so this is the component, or this is the buffer space. This is the space in the ring buffer in which the data is read. Okay, so data yet to be read, the data which is to be read. Read pointer is basically mean you can read it as a read pointer. Okay, the data which is already read by the media pipeline. Okay, address where data can be overwritten. So the data is already read, so the data can be written here. So the write pointer can write the data again here. Now to support the 0 copy reads, we need that mechanism, right? We need that implementation in place. Feed frames from peek pointer to media pipeline. Okay, advance the read pointer when frame is fully processed. Great. we already understood what are the use case of these 3 pointers. Okay, so you are feeding the frames from peak pointer to media pipeline. Okay, so this peak pointer will feed the frames to media pipeline. Advanced read pointer when frame is fully processed. Okay, when frame is fully processed, let's say this frame is fully processed, which means the data is already read. In this case, you can advance this read pointer because it can be allowed for the overwritten. Great. Another thing is there are atomic operations to update the pointers in threads of manner, so that if the data is written by multiple, because it's written by multiple threads, right? So the operations are atomic. All the update operations or all the write operations are atomic, so that everything executed in threads of manner. We also needed a mechanism so that your media processing pipeline can know that a new data is written. Okay, so in that case, you need use a named semaphore. Named semaphore is basically your semaphore which is identifiable by a name. And semaphore, if you don't know, you might have again studied this in your college curriculum, in which we studied about mutex and semaphore. Okay, mutex was basically mutual exclusion, where you take a lock, and semaphore was a signaling mechanism which you use for signaling purposes. Okay, so this is all we are discussing today. I hope you understood it. I hope you learned something new which you generally do not learn for your interviews or understand for your interviews or dive deep for your interviews. But we will meet again in a new video. But before that, if you haven't subscribed to the channel MsDeep Singh, consider subscribing. If you haven't looked at the book System Design on AWS, if you are not actually trying to buy or not actually thinking to buy the book, just check the table of contents of the book. Okay, table of contents, just check that. You will see there is a lot of content from which you can learn and then become a better software engineer or architect. Okay, so we will meet again in a new video, in a new discussion video. We will be diving deep into new architectures. Till then, stay safe. Tata, bye bye.